Relationships between sets. When two sets are compared with each other, several possible kinds of relationship may be observed. If two sets S1 and S2 happen to contain identical elements, S1 equals to 2, 7, A, F, and S2 equals to 2, A, 7, F. Then S1 and S2 are said to be equal. S1 equals to S2. Note that the order of appearance of the elements in a set is immaterial. So, the matter of orderance or the order in the two sets is the not matter. But whenever we find even one elements to be different in any two sets, however, those two sets are not equal. But the condition is the same elements in the two sets without the order. Another kind of set relationship is that one set may be a subset of another set. So one is the equal set. Another type of relationship is the subset. Okay, S equals to 1, 3, 5, 7, 9, and T equals to 3, 7. Then T is the subset of the S set. Then T is a subset of S because every element of T is also an element of S. A more formal statement of this is T is a subset of S if and only if X epsilon T implies X epsilon S. Using the set inclusion symbol is contained in and includes, we may then write S is greater than T and the S is or S greater than T. It is possible that two given sets happen to be subsets of each other. When this occurs, however, we can be sure that these two sets are equal. To state this formally, we can have S1 equals to S2 and the S2 is the S1 equals to S1 if and only if S1 equals to S2. Note that whereas the epsilon symbol relates an individual elements to a set, the epsilon symbol relates a subset to a set. As an application of this idea, we may state on the basis of that the set of all integers is a subset of the set of all rational numbers. Similarly, the set of all rational numbers is a subset of the set of all real numbers. How many subsets can be formed from the 5 elements in the set S equals to 1, 3, 5, 7, 9? First of all, each individual element of S can count as a distinct subset of S, such as 1 and 3, but so can any pair, triple, or quadruple of these elements, such as 1, 3, 1, 5, and 3, 7, 9. Any subset that does not contain all the elements of S is called a proper subset of S. So, the set S1357 includes. So, any subset which not includes the complete, like in the above, in the former, they contains 5 elements. So, any subset which not contain all the elements of the set is the known as the proper subset of a S. But the set yes itself with all its 5 elements can also be considered as one of its own subsets. Every element of S is an element of S, and thus the set S itself fulfills the definition of a set. This is, of course, a limiting case that from which we get the largest possible subset of S, namely S itself. At the other extreme, the smallest possible subset of S is a set that contains no elements at all. Such a set is called as the null set or the empty set, denoted by the symbol empty brackets. The reason for considering the null set as a subset of S is quite interesting. If the null set is not a subset of S, then null set must contain at least one element X such that X not equal or equals to S. But since by definition the null set has no elements whatsoever, we cannot say that. Hence, the null set is a subset of S.